Physical science time. Let's talk about atoms. Surprisingly, this marker is worse than the one I just replaced it for, but whatever. Before we talk about atoms, even though we've just titled this atoms, let's talk about the four fundamental forces of the universe once again. Four, oh goodness, marker. Fundamental forces of the universe. Okay, Wade, you only have said one word so far, but I would politely ask you that before you're going to speak, would you please raise your hand, okay? I do want your contribution. I just want to know what's going to happen and not be cut off mid-sentence.
Sorry. Well, there goes that video.
Let's order these four fundamental forces in the universe from the strongest on top to the weakest on bottom. And we've talked about this before, but in addition to being ordered from top to bottom, strongest to weakest, what is their order going to be from bottom to top? Do you remember?
The distance.
Yeah, the range. They will be from bottom to top, they will be longest range to shortest range. So let's just go ahead and label that right away. From top to bottom, they are strong up here, weak down here, and from bottom to top, they are long range down here and short range up here. The first, meaning the strongest and shortest range, is, do you remember?
Strong nuclear.
Strong nuclear force. Write that down, please. Strong nuclear force. Do you remember its job, or I always say job, you should understand before, as we go into this, that these things don't have jobs in the sense that they are intending to do something and they feel satisfied when they complete it, as you have a job. I mean their role in the universe, right? Not that they have decided that, but that's the way it is, what they do in the universe. What does a strong nuclear force do? Did we talk about this ever? So write this down. The strong nuclear force we can think of as the energy that holds together protons and neutrons in the nucleus. I'm going to put that in parentheses. Holds together protons and neutrons in the what?
Nucleus.
Nucleus. Holds together protons and neutrons in the nucleus. And I don't know if you, one thing that helps me remember this is that we know that the electromagnetic force does what with similar polarities of electromagnetism. Meaning positive and positive do what? Negative and negative do the same thing, which is repel. Repel. Opposites attract, but the same charge repels. So if we think about the nucleus of the atom, and it's entirely made of what two things, as you already know from 6th grade, Mrs. Steck? Protons and neutrons. The nucleus is entirely made of protons and neutrons. What then is attracting? Yeah, I don't know. This is what helps me remember the strong nuclear force, because electromagnetism, the force that acts on just those, just the positive and neutral charges in the nucleus, would have them do what? If there was no strong force, what would they do?
Repel.
Yeah, they'd all repel. The nucleus would explode, in fact. So this is stronger, we can remember, than the electromagnetic force, because they're kind of serving opposite functions here. In fact, when we get to chapter 18, which is about radiation, it becomes apparent that in very large nuclei, that's the plural of nucleus, in very large nuclei, this, since it has a shorter range from one end of the atom to the other, doesn't act as strongly as the electromagnetic force, and so the thing does fall apart. That's really all radiation is, or nuclear radiation is. The weak nuclear force. The weak nuclear force. I think when we talked about this the first time, I said, it's spooky quantum mechanics stuff, don't worry about it right now. It still is. We will talk more about this in chapter 18, but effectively, this governs some types of what we call beta decay in the nucleus. This is a force that can and sometimes does cause protons to become neutrons or neutrons to become protons. I'm not going to write that down right here because unlike the strong nuclear force, it's not immediately important to us in this chapter. We will revisit this and talk about it again in chapter 18.
I thought that the electromagnetic force was...
Oh, you might be right. Did I give you the list at the beginning of the year that was SUG? Yeah, okay, so 3 should be the weak nuclear. Please forgive me. Let's cram electromagnetic in there as number 2. Thank you, Haley. I'm at the same time embarrassed and appreciative. There should be a name for that emotion. Like when someone tells you that your fly is down. That's how I feel right now because she's right, and I do appreciate you telling me this. but I'm also embarrassed by it. So electromagnetic force, which we're also not going to go, good thing too because I don't have room, but we're not going to go into detail on that because I don't know if you remember, but we spent like 3 chapters on this, right? We should know about the electromagnetic force a little bit by now, right? Do you remember this?
Yeah.
Yeah, magnetism. We talked about how the north and south poles of a magnet do what?
Oh,
No,
Attract.
attract, sorry. They're opposites.
They're opposites, and so they attract. It's the same force that governs the positive and negative charges attracting in the atom as the north and south poles of a magnet attracting. And then the weakest and the longest range is gravity. These are all what we call field forces. Another name for a field force is a non-contact force. All of these are technically universal. It's just that they drop off. For instance, the strong nuclear force drops off very, very quickly. If we were to graph the strength of the strong nuclear force, we could have strength over here in, what would we measure the strength of a force in? No, come on. Newtons. The strength in newtons compared to the distance in, we're going to say something called picometers, which is, picometer is kind of like 1 atom is about a picometer.
That's small?
Yeah. The strong nuclear force drops off extremely quickly, so it's really the strongest, but it drops off really fast. Did you ever figure out what this word was called, where it approaches 0 but never actually reaches 0?
Yes.
Okay, what is it then?
All of them figured out.
Okay,
Near
so
0.
you didn't.
I don't know.
I did.
Near 0.
It's an asymptote. So technically, you could never measure it. There's no instrument strong enough to measure this. But technically, because they're all field and non-contact forces, technically a proton in my podium is attracted to a neutron in this thing, right? It's for the strong force, that's an extremely long range, and there's no measurable attraction between them. But technically, because it's an asymptote, it is technically true. Do you see what I mean? It's so infinitesimally small that we could never measure it. And even over the width of a normal size, like maybe, I'm going to be pointing at the people a lot, even though no one on the video can see it. For instance, if we look at like a chromium atom, which has 52, sometimes it can have 52 little particles in its nucleus, protons and neutrons together. Over the width of that thing, it probably is about half as strong from one on this side to the other, because it drops off very, very quickly.
What do you think of that?
Whereas gravity, we might draw a much, much shallower curve. It's still strong over very large scales, right? You could be, we just talked in physics about the International Space Station orbiting Earth today. The International Space Station experiences gravity about 95% as strong as the gravity you experience here on planet Earth, and even though it's hundreds of thousands of kilometers away from planet Earth, right? So gravity drops off much more slowly, okay? Do you have questions about any of this so far? These are called the what? Yeah, we all kind of said it, good enough. And you need to know these, what they do. You know what gravity does. Gravity attracts all what?
Everything.
Mass.
All masses in the universe. Everything that's matter in the universe is attracted to every other thing in the universe by gravity. We will talk about the weak nuclear force more in chapter 18, which is about nuclear radiation. We have talked about the electromagnetic force, and what I expect you to remember about that is that the opposite electromagnetic charges attract, and similar electromagnetic charges repel. And then we're going to talk a little bit more about the strong nuclear force here in a second, but this effectively, as I put here, is the energy that holds together the protons and neutrons in the nucleus. It's more than that. It's also the energy, you can write this down, this will be your first bullet point. It's also the energy that holds the quarks together in the nucleus. For instance, we know, I think, Mitchell, you were here for this, in our maps science time, we talked about quarks a little bit. Was anyone else here? You were here too, Lily, right? And Haley, you were here, because you made me that statement. I don't know.
I was in here for map science.
Were you here last time?
No, you weren't. Were you?
Were you?
Yeah, science. You
You
mean
I
science,
too,
not
so probably
math?
not.
It would have been science.
Wait, what about?
Anyway,
None of them were.
please calm down, please calm down. Quarks make up the protons and neutrons in the nucleus. So let's write that down first as our first point. Quarks. Oh, good question.
I don't know.
Q-U-A-R-K-S.
This is not really a very good marker, but this says Q-U-A-R-K-S. Q-U-A-R-K-S. Quarks.
What?
We're getting there in one second.
Okay.
Quarks. Quarks are the particles that make up protons and neutrons. Make up protons and neutrons.
So they're pretty much
I feel like
protons.
that's gonna be on the test.
I feel like you're right. There are 6 kinds of quarks. I'm going to draw them up here. This is not how I really wanted things to progress, but there are 6 kinds of quarks. 1, 2, 3, 4, 5, 6. Oh, hey, if you see a list like this when we're taking notes, what do you guess might be on the test?
Yeah.
Probably a list like this. The quarks are called up, down, top, bottom, strange, and charm. Up, down, top, bottom, strange, and charm. These are the quarks. These are not the only particles in the universe, but they are the particles that make up the nuclei of all matter in the universe.
Charm.
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 Charm. Up, down.
C-H-A-R-M.
A-R-N.
Shh, please.
M. As in Mitchell.
Hey, be calm.
Well,
Shh, don't.
I'm
Okay,
pretty sure it
let's-
says
I'm going to remind you, as I reminded way at the beginning, if you have something to say, I want you to say it. I need you to raise your hand first because I'm getting a little. So raise your hand first and then we'll talk about it. So the 6 kinds of quarks are up, down, top, bottom, strange, and charm. These 2, up and down, make up all normal, what we call normal, matter in the universe. It's not quite true because all normal matter in the universe is made out of some combination of these 2 things, making up the protons and neutrons, and also another little boy called the, what else is in there? In the atom? The electron. The electron, which is a lepton. We're not going to talk about leptons today, but if you're interested, you can sometimes look up, but an electron is a kind of lepton. Anyway, we're not going to worry about that too much. So all normal matter in the universe is made out of some combination of these 2 quarks plus an electron. Okay? That's what makes up what we call a or an what?
Atom.
Atom. So an atom, now we're getting to the stuff that you've heard about in 6th grade. Atom is made of 3 things. What are they? And let's tell for each of the 3 things, we're going to say its name. The 3 things that make up the atom I'm talking about. The name, the location, the mass, and the charge. Charge is over here. I printed it in the corner a little bit, but you understand. What should be the first one we do?
Proton.
Good idea. Let's do a proton. Proton, sometimes we abbreviate this with a lowercase p.
what is the last one?
Charge.
Charge.
Where's his location? The reason I'm asking you this instead of telling you is because I have intuited from you that you already know. Where is the location? Nucleus. So, wait, if you don't know it, don't say it, okay? Relative mass. Relative mass. Small. Small. Let's just put 1. 1, what we call atomic mass unit. AMU. Atomic mass unit. If you need to write down what AMU stands for, write it down somewhere. What does it stand for?
Atomic mass unit.
Atomic mass unit. And it's charge.
That's charm.
Plus
Oh my God.
plus 1. Let's put plus 1.
It says charm.
Hey,
I was telling you.
moving on to the next one.
Neutron.
Neutron. Where is he located? Where is she located? Kyla wants me to be non-sexist. Oh, first, how can we probably abbreviate neutron? If we abbreviated proton lowercase p, neutron might be
Lowercase n.
sure. Lowercase n. Location?
Nucleus.
And also in the nucleus. And these 2 things are held together and to each other by what force? Strong nuclear force. Good, you got it. Mass? How do you think it relates to the mass of a proton?
I think it's probably the same.
It's the same. 1 AMU.
So charge is negative.
You can't see this on the camera, but I'm going to read you these things. Mass of proton, ready? I'm just reading it to you, and so you can hear it. And there's no way you can. Occasionally, might be able to read this, but the rest of you are too far away, and the YouTube video isn't going to see it. But shh, I'm going to read it to you. Mass of the neutron in kilograms: 1.674927 times 10 to the negative 27th kilograms. Okay, and then the mass of the proton is 1.672622 times 10 to the negative 27th kilograms. So until we get to the 10,000th place, they are the same. We consider both of them to have a mass of 1 atomic mass unit. In fact, we define, stop. We define, I said stop, don't keep doing it after I told you that, okay? we define an atomic mass unit as the average of those two things. They're very similar in mass, and so when we talk about their mass in AMU, this AMU is defined as the average between those. So an atomic mass unit then is 1.66052 times 10 to the negative 27 kilograms. Okay? What do you think the charge of the neutron is?
0.
Yeah, no charge. You can put neutral, but 0 charge since we put 1 for the other one. And then lastly, electron. Lowercase e, and then you have a little, sometimes I've seen it both ways. Please stop talking. Please stop talking. I've seen it abbreviated both ways. Lowercase e with a line above it, and lowercase e with a little superscript of negative sign. I put a little negative sign in mine. So a little e with a little negative sign. Where's the location of the electron?
Outside the electron.
Yeah, we sometimes call it an electron field, we sometimes call it an electron cloud. Sometimes in older models of the atom, and sometimes still for illustrative purposes, we might call it in orbitals. But I'm just going to for now put outside the nucleus. Outside the nucleus. Mass? Usually we consider it we consider to have negligible mass. But I'm going to put 0 for this. If you read up here and you did the math of the electron is 9.109383 times 10 to the negative 31st kilograms, which comes out to about 1/1800th the mass of the other two. And because the math we're going to be doing with these and the math we generally do with all three of them involves how they compare, there's never going to be 1,800 electrons to make up the difference. Even, because of rounding, if we even had 900 electrons, we would round that up to 1 AMU, right? But we never have 900 electrons in any given atom, and that's what we're going to be doing the math with. So we consider their mass to be 0, okay? Charge, though? -1. Peyton.
What was the one thing that's a type of, and that it was a
Lepton. An electron is a type of lepton. You can read about the other 4 types of quarks, but especially these two, they get heavier as we go down, and especially these two are found in really kind of bizarre matter. There's some, I don't remember, it's been a long time since I read about this, but there are some hypotheses of the universe that there might be some stars that are made out of strange quarks entirely, and there's some hypotheses that if there was ever strange matter in the universe on any large scale, that eventually all the matter in the universe would become strange matter. And it's kind of interesting, but not really what we're going to talk about today. The next thing we are going to talk about is how the quarks combine to form the protons and neutrons. So we know that the protons have a charge of +1, we know the neutrons have a charge of nothing, but what we don't know yet is the up and down quarks have charges as well. So an up quark has a charge of positive 2/3. And a down quark has a charge of negative 1/3. So write those down first. Those are facts. As I understand it, this is more of like a bookkeeping tool. Like these things are considered to have these charges so that they turn out right when we add them together. But it's still kind of interesting. Yes, Peyton?
So the only thing it does is it just doesn't go under strong interaction.
The lepton has significantly less mass than the quarks do, significantly. But no, it does not undergo the strong interaction. In fact, it does undergo, though, what kind of interactions does an electron have? We can tell from its charge. No, it doesn't have strong interaction. It has
Weak.
no, what other force does it interact with?
Electron.
Electromagnetic, right? Anyway, so because the quarks that we're going to deal with in normal matter have an up and a down nature, and we call those a positive 2/3 charge and a negative 2/3 charge, let's see what happens when we add them together. Every nucleon is what we sometimes call these two together, nucleon, because they exist in the nucleus. Every nucleon is made of 3 quarks. So what combination of this math could we do to get a charge of 1? How could we add these? We need 3 of them. How can we add them together to make a charge of 1? 2 ups and a down. So if we have 2 ups and a down, up, up, down. This is like a really weird face. The ups together will add to a charge of what? 1. No, just the ups. Yeah, 4/3, right? So 1 and a third. And then we're going to subtract 1/3, which will give us a charge of what? 1. That's nice. So that makes a proton. And I'm going to draw these little wavy lines between. What does the wavy line represent, do you think?
The wave, the mechanical wave.
Someone said that, I think. Say what you said.
Connection.
No, it's not the electromagnetic force.
Mechanical wave.
No.
Connection.
Yeah, what is making up? What's connecting them together, though?
Gravity.
No, not gravity.
Strong.
The strong nuclear force. Didn't I already tell you that this pulls together the quarks too? Yeah. So the strong nuclear force. This little wavy line that connects them is called the strong nuclear force. Now, if instead we wanted a neutron, what would it be made out of?
Neutron.
No. What quarks would it be made out of?
Down.
Yeah, 2 downs and 1 up. Still held together with a strong nuclear force, but now we have negative 1/3 and negative 1/3 and positive 2/3, which adds up to, as you can tell, 0. So protons are made of 2 ups and a down, and neutrons are made of 2 downs and an up.
This sounds like a cheat.
A little bit. As we know from watching our video and from we discussed this before, it hasn't always been understood that matter is made out of this stuff, right? Like this is a fairly recent innovation. In ancient history, people thought that all matter was made of what?
The element.
Yeah, the 4 classic elements. Fire, water, earth, and air, right? All that matter was made of the 4 classic elements. We know that that's not true now. None of those 3 things is an actual element. But over time, what we call the atomic model, how we think about the way matter is made up, has changed. And so let's talk about that for a second. This is really not doing a very hot job erasing this. I gotta use one of my little erasers. Atomic model, write this down please. Atomic models. The first thing I've ever heard called an atomic model, the things I've heard called atomic models, the one that occurred first in human history was someone called Democritus, who was an ancient Greek. Democritus' model. And I'm going to put model in quotes because the way we understand models in science now is that it's some representation of the way things actually are, but we know that it's not exactly right. So for instance, if we had a model airplane, right? We might look at that model airplane and understand that it represents the way an airplane is, but obviously it's not a perfect representation. Why? What might be imperfect about a model airplane compared to the real thing?
It's not the same size.
It's not the same size, obviously. What else?
It probably won't fly.
Probably doesn't fly, probably doesn't have an engine, probably doesn't have a little good control lever. Some of the really good models might have all those details, but even if it did, it probably isn't going to fly, right? So we know that models in science are always flawed, but they're representations that we use to understand real world objects. Democritus doesn't even really cut that mustard because it's not really a model. He just kind of had a thought experiment, which was, the way I've heard it, and this is probably apocryphal, but the way I've heard it is that he had some cheese or an apple or something you could cut, and he cut it in half, cut one of the halves in half, cut that half in half, and kept doing that, and he thought, over the course of whatever, a day, it was ancient Greece, he didn't have anything better to do, so he just cut all this up. He thought, there must be at some point something that's uncuttable, right? And so he called that atomos, which is Greek for to cut. A, means with what? What does A mean in Greek? Like asexual reproduction means reproduction without sex. Reproduction without sex. So A means without. Without or not, or without being able to. And then tomos meaning cut. So he called it an atom, meaning that it was the thing that couldn't be cut. But like I said, it was just a thought experiment, right? So he thought, what if there was something that couldn't be cut? I'm going to call it an atom. So really all he did was kind of come up with the name. For a long time in between this and the next one, what we call the classical idea of matter was prevalent. Sometimes called the Aristotelian idea of matter because someone called Aristotle thought of it, which was that all matter was made of fire, water, earth, air, and then something he called quintessence, which was the 5th element. That doesn't matter because that was wrong. So after a long time though, it was found with the Thomson model, J.J. Thomson found that when matter combines, it had been known for a while by this point, this was in the early 1900s, it had been known for a while that matter wasn't composed of fire, water, earth, and air, and in fact it was composed of some of these elements had been discovered. We saw in our video that Antoine Lavoisier discovered several, barium had been discovered, all these different elements had been discovered by people in sometime around the late 1600s to early 1800s. A lot of elements were discovered, right? So they knew about elements, and they knew them as elements, but this Thomson model was the first to come up with the idea that the atoms that make it up could combine in these ratios. And so what he did was he found that when they combine, elements always combine in set ratios. So he just had the idea, set ratios in chemical reactions. And that was his evidence, and that's the key bit of this, that Democritus didn't have any evidence for his, right? His was just a thought experiment. But Thomson had evidence that suggested that maybe matter really is composed of something that cannot be cut apart, that can't be separated anymore, right? So he called that, he named it after Democritus' idea of an atom. To him, it was just indivisible particles. Just perfect spheres of oxygen, or chlorine, or mercury, or whatever, right? Gold, anything. We knew what the elements were, and he had this idea of these just solid, perfect spheres of just matter, right? Of just that element. Next came the Plum pudding model. And this was...
Yeah.
This was because it was discovered that actually much of the atom was made of positive and negative.
Thomson did discover this one too, right?
Oh, was this Thomson's model as
Yes.
well? I might have misnamed the first one.
Yes, no, that one.
What?
This one you're talking about is Thomson.
What was the first one that I was just talking about called?
I don't know, but this one is.
Erase Thomson, because the first one we just said might not have been called the Thomson model.
Because this one.
The Plum pudding model is also the Thomson model, you're saying?
Yeah, because this one has very black.
Okay, perfect. That's okay, I believe you. So we'll call this one the Plum pudding model now. Leave that one like, oh, Dalton. I'm sorry, I forgot. This one's called Dalton.
Dalton what?
Dalton's model. The Plum pudding model, Payne is exactly right. The Plum pudding model is also called the Thomson model. But it was discovered that the atom had both a positive and negative parts, right, which we now know as protons and neutrons. But to him, he just put them in this. It's called the Plum pudding model usually, but I like to think of it like a chocolate chip cookie model. So to him, it was this positive matrix, the positive cookie, with little inclusions of negative chips in it, right? So that was his idea. And then can you imagine what the next thing that was discovered might have been? This next one we call the Rutherford model. But what's the glaring thing that's wrong with that compared to what we know? Yeah, it doesn't have a nucleus. There's not enough what? This is still a solid lump like these were. So there's not enough space. There's not enough space. So Rutherford's model, like you said, by Ernst Rutherford, was the first to discover that there was a nucleus surrounded by, and this is when you see like Jimmy Neutron or like the symbol for atomic energy, the classic, like how we
Big Bang
think
Theory.
an atom is. Yeah, that stupid show. The classic how we think of what an atom looks like, or if you type into clip art or Google Images atom, this will come up, and this is the Rutherford model. So the main difference, like this little sticker I have here is a representation of Rutherford's model.
I read something that
Shh,
said,
give me a second to speak. The main difference here is that, as Wade said, the nucleus now is separate from the electrons. And what might have been discovered between here and here that led to this model being created?
A nucleus?
Well, it's more simple than that. Basically what he did, Rutherford and his assistant had this sheet of gold foil, and they just fired radiation at it, and they thought that if the sheet of gold foil were made of these solid spheres, most of the radiation would just bounce back. What they actually found is that most of the radiation went straight through, which leads them to believe that the atom is actually mostly empty space. And so you should write that down. The atom, we know this from the Rutherford model, but it's been tested time and again since then. The atom is mostly empty space, almost entirely. In fact, if the illustration I a lot of times use is that if the nucleus was a basketball in the center of a football field, the electrons would be the size of little peas, and they'd be orbiting a good portion of a mile away, probably at least 200 yards away, depending on their energy level. But it's mostly empty space. It's almost entirely empty space, and we know that from Rutherford's experiment. In fact, what was cool about his experiment is they were able to calculate how much of it did bounce back, how much of it got through, and how much of it was reflected, or how much of it was deflected in different directions. And so using that information, they could tell that the atom was 97% empty space, or whatever it is. You see what I mean? Okay, after that, after the Rutherford model, do you have a question, Peyton?
No, I was gonna say something about that.
Is it about this Rutherford's model?
It's about the Plum pudding. And,
Oh, okay, let's hear it, quickly.
So Ernest Rutherford was J.J. Thomson, one of his students.
Oh, okay, that's interesting.
And Rutherford proved that J.J. Thomson's part of it was wrong because it didn't show
Right, 'cause-
positively charged.
Right, because the nucleus was the positively charged center of the in mostly empty space. That's interesting. So what Peyton points out is that Rutherford was Thomson's experiment, and so effectively, the student proves the master wrong. That's very interesting, just like in Star Wars. Okay, we're moving on now to the Bohr model. Bohr model. I made this H kind of weird. It's B-O-H-R, and the main difference here is that it was discovered that atoms actually have energy levels of electrons. So while we still knew it was mostly empty space, we now understood that the electrons,
That's a lot of electrons.
the electrons separate themselves into what we call
A
energy
orbit.
levels, into what are sometimes called orbits. So electrons have discrete energy levels. We use the word discrete, which in this case there are two ways that you can spell and mean discrete. Discrete can mean sneaky, like when you discreetly sneak out of the house to be with your boyfriend. Ooh, that's discrete. But it also, spelled a different way, means individual. So they have discrete levels. They have a level 1 and a level 2. An electron can exist in level 1 or 2, but nowhere in between, right? Kind of like stairs. You can exist on stair 1 or stair 2, but you can't be on stair 1 1/3 because there's nothing there, right? So that's what discrete means in this case. So the Bohr model illustrates that the energy levels, we say, of the electrons are quantized, which means that they exist in discrete levels. And then the final model that we use today is the...
the properties of the element. The orbit determines the properties.
Right, yeah, so we'll talk about valence electrons in the next lesson. Thank you, though. What we now call the electron cloud model, coupled with something called the quantum mechanical model.
Who is found this one?
A whole team of people at Berkeley, I think, but I don't know exactly. Just type in cloud model. This one is very similar to the Bohr model. We know that there are electron orbitals, but they aren't shaped like this. What they instead are is this kind of hazy area around the nucleus where electrons can exist. What's called the electron probability cloud. It's an area where an electron is able to or might exist. There's still energy levels, and we'll talk about why that is if not this chapter, then chapter 18. But effectively, instead of this model, the Bohr model leads us to believe that the electrons are actually orbiting, like planets around the sun, for instance. They don't. We know now that how they move is they stop existing in one place and they begin existing in another place. There is no motion. So unlike you, they're teleporting. Yeah. Unlike you, if I want to go to the microphone, I have to spend some time in the space in between where I was and the microphone, right? That's not the same for electrons. And we know from various experiments that the electrons just simply stop existing in one place and start existing in another. And the reason for that is kind of the same as, we talked about this in the maps science thing too. Electrons are not particles as such, they're what we call excitations in an energy field. And so in the same way that an ocean wave might seem to stop existing in one place and then start existing in another, but it's not really, right? It's just because the whole thing is one medium. And it's excited over here, and then it changes and it's excited over here. Same thing with this. The electrons are just an electromagnetic field, and at 1 second there might be an excitation here, and then when that simmers down it might pop up over here. And so it seems to us like teleportation until we realize they're not actually particles. They're not stuff. They're energy.
So you can never know where it is at a given
Yep,
time.
and we are going to talk about that. That's called the Heisenberg uncertainty principle. We will talk about that. Do you have questions? So the things that I want you to know from today as a summary, the 4 fundamental forces of the universe, you must know and memorize those. Questions about any of that? You must it was down here. You have to know the location, mass, charge, and name of all 3 subatomic particles. You must know all 6 quarks, especially the up and down quarks, and that those 2 make up the universe. And then you need to be somewhat familiar with the different models of the electrons, or sorry, the models of the atom. Do you have questions about any of that? If you do, please raise your hand. Many of you just asked them without raising your hand all throughout the lesson, but yes.
Never mind.
All right. Other questions besides weights that he has elected not to say?